the spatial representation of a free group has a property over S2 complex that it's actually an irreducible variety of dimension 3 times n. So nth of 3 times n of r sub a of g is equal to 1. Okay? So that's what our function is. So this immediately raises all kinds of questions about Parafree groups. You know, right away after seeing this, you know that there's only one component of dimension 3n. You know right away that, in fact, this stuff admits a group structure. Because it admits a group structure, it's going to become a smooth object. You can find tangent spaces, you know, at every point, no problem. So, you know, you have here a, you know, a very wild thing. And now you can actually say, well, look, I am going to look at Parafree groups using all the possible invariants I can imagine. And I want to just start publishing like crazy. But anyway, some people don't like that. So, so these are some of the questions that, you know, that you can ask about Parafree groups. For example, if G is Parafree of rank n, is the dimension of the spatial representation of G equal to 3n? Okay? How many non-isomorphic representative varieties of Parafree groups of the same rank are there? Remember that up to isomorphism, there is only one representative variety of a free group of rank n. Only one. So if you have a Parafree group of rank, let's say 2 and deviation 1, you can say, how many non-isomorphic representative varieties are there? Right? How many are there? Maybe 1. That would be wonderful. That would be just wonderful. You can say, you know, if G is Parafree of rank n is the function n sub d of r sub a of g equal to 1. That means, is there only one irreducible component of the dimension of the algebraic variety, as is the case in the free group? You can say, again, we can show, as I said, that the spatial representation of a free group is actually smooth. Is the same the case for Parafree groups? Okay, so we're going to try to answer all those questions.
Completely different question I have. What about decision powers? Do you know anything about
For algebraic varieties?
For Parafree groups?
I cannot answer that question. I don't think that that's an established
Question.
that has been established yet with the isomorphism problem holds for them, and of course that is a good reason to study this. I mean, whether the isomorphism problem has been solved for them, whether I don't know. No. Okay. I can tell you that finally presented ones, for example, has solvable word problem because they are residually nilpotent and nilpotent groups that are finally generated. No.
It might have some torsion.
Well, no, but if they're finally presented, I think that they have solvable. They have solvable.
In general, the isomorphism problem is solvable for now.
No, I'm not talking about.
Everything's solved.
I am venturing outside, you know, my realm, and I'm going to be broadcast all over the world. So.
Everything is solvable for residually?
No, for now.
Oh, yeah.
Okay, so then those are good questions actually, very good questions. Thank you, Delara, for asking that question. So we have all these questions that need to be addressed, and you know we're hoping that because we're so close to freeness here that these questions are all answerable in a nice way that keeps us believing in the similarity, the sort of free-likeness of the free-like properties of Parafree groups. We want to see that. So now, deviation and dimension, I really could go and talk about this for a while, but maybe I want to sort of make it brief. So we can actually provide a bound for the dimension of the representative variety of a Parafree group of rank n and deviation. Okay, I don't have to say SL2 complex. I can use any other affine group, but I am staying with XL2 complex now. And this is the theorem. If G is a Parafree group of rank n and deviation k greater or equal to 1, then the dimension of the space representation of G over A is smaller or equal to 3 times n plus k. It's strictly smaller. Sorry, strictly smaller. I said smaller than or equal. I mean strictly smaller. So this gives you a bound, the dimension, using the deviation. Now, I don't want to go through the proof, because, you know. Okay, so now let's answer all those questions that were asked. Okay? We're going to answer all those questions that were asked, and we're going to answer them in a very devastating fashion. So let me actually sit down, because I have to actually take you through this.
Yes, we'll sit down.
I have to sit down because, you know, I have to actually take you through this. Okay, this is my theorem of 2006. Okay, given an integer k, there exists an infinite set S sub k consisting of Parafree groups of rank 2 and deviation k, having the property that for Gi and Gj in this set, infinite set, with I not equal to j, the following holds. The dimension of the space representation of G sub j, G sub I does not equal the dimension of the space representation of G sub j. Okay? I'm sorry, equals the dimension of the space representation of j, and this is equal to 4 plus 2k. Okay, that means that if I take k to be equal to 4, the dimension is going to shoot up. If I take k, if I take the deviation to be 7, the dimension is going to shoot up. So here we have Parafree groups of rank 2 with dimensions as large as you desire. As large as you want the dimension, you can make it. Look what's happening. I mean, this is insane. Parafree groups are supposed to be like free groups, right? Well, they're not. As far as this is concerned, they are absolutely not. Let's continue with this theorem. If we let C equal to 4 plus 2k, then the algebraic variety, R sub A of Gi, does not equal the algebraic variety, or it's not isomorphic. The number of 4 plus 2k irreducible components of the algebraic variety R sub A of Gi does not equal to the number of 4 plus 2k irreducible components of the algebraic variety R sub A of Gj. In other words, the component structure, okay, is completely different. This tells you they're not isomorphic. Okay? And in fact, it can even get worse. It says given any integer m, there exists an infinite subset Q in S sub k, such that for any G sub t in this set Q and C as above, the number of maximal irreducible components in dimension C is greater or equal to that number. Okay? So in essence, something is missing here, and as in essence, this thing is very, very, very different. These groups are very different from free groups. You know, these algebraic varieties cannot be isomorphic. You can make them have as many components as you want. If you ask me, could you find a Parafree group of rank 2 with 1 billion irreducible components? I can find one for you right away. You know, I mean, this is actually a very sad situation. But it's also, I did not do it because I wanted to get sad. I did it because I wanted to actually find, I wanted to take my invariant to the limit, and I did it. And that's it. The invariant has been taken to the limit. Now I can just move on and do more interesting things. Okay? And this is what we're going to do. And I could go over the proof, but I don't want to deal with that at this point. I could actually come back. Now, but I do want to actually explain to you, okay, how part of this thing was obtained. And partially I want to explain to you this because I do like this mathematician. His name was Eratosthenes, and he worked in the 3rd century BC in Alexandria, and he has a famous theorem about, well, it's not a theorem. He gives a procedure for counting, for listing all the prime numbers. And one day I was kind of, hanging around in some library, and I found, I found, this, and I began to look at it, and I said, oh my God, I want to use something like that. I really want to use something like that. Because I really, he did a lot of wonderful things, but, this is one of the things he did, so I decided I am going to use him as an inspiration for this particular, the prime number sieve, as a way of finding an infinite number of non-isomorphic algebraic varieties. So I began to work on that, and eventually I came up with the so-called coarse sieve theorem, which actually has its origin there, in the work of probably Eratosthenes. So essentially, what the coarse sieve theorem does is that if you have an infinite sequence of pairs, pairs consisting of a group G sub I and a normal subgroup N sub I. You have an infinite sequence, a very horrendous object, and here it is. So we have finitely generated groups, G sub I, and a corresponding normal subgroup N sub I of G sub I. And now we let n sub C of D, be the irreducible component counting function in dimension C, and suppose that this is the case, that for this whole sequence, this infinite sequence, you have the dimension of the space representation of G sub I is equal to the dimension of the space representation of G sub I modular normal closure, modular normal subgroup N sub I, and this is equal to C. And suppose that this set here has an infinite number of integral points, of integer points. Then, right away, you can conclude using the coarse sieve theorem that this sequence here has an infinite subsequence S squared with a property that given two different pairs, here in S squared, then the number of C-dimensional irreducible components of this algebraic variety are different. So this gives you an infinite number of non-isomorphic algebraic varieties, representation variety. And this is the way I actually, it was really I should really say that it was really Eratosthenes that actually gave me the idea that I could actually do that, because I was looking at that, I didn't have to teach, so I could actually just focus on some crazy stuff like that. Where other people were teaching. I really feel bad.
Yeah, I know you feel bad. Thank you.
Yeah, but anyway, so I did that. But anyway, so that was my tribute to Eratosthenes. Okay, so here it is. So this algebraic varieties are not isomorphic. And of course, then we can. Then the theorem says that you can well order the set S of 2. And that was really it. So now we're ready to introduce the profile function. The profile function allows you to generalize a lot of stuff. And I still have 15 minutes, so I can slow down. So the profile function is something that we dreamt up. I don't know how it happened. We dreamt it up. The profile function is defined as P sub D, R sub A of G. So where D is equal to the dimension of R sub A of G. So now let's see what the profile function is. We're going to define what the profile function is. So what we're going to do is, let me sit down because this takes a little bit of verbosity. So given an algebraic variety, suppose you're an algebraic variety, Delaroche. So P sub D of U is going to ask you, Delaroche, how many components of dimension D do you have? How many components of dimension D minus 1 do you have? How many components of dimension D minus 2 do you have? How many components of dimension D minus 3 do you have? How many components of dimension D minus... How many components of dimension 0 do you have? So you are going to answer.
Well, I'm not a computer.
No.
I'm a group.
Well, no. You're not, I said that you were an algebraic variety. So you have been asked this question, right? So this is an invariant of groups, and using this invariant, you can actually generalize a lot, and you can basically